Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 6.2 from your textbook, which introduces you guys to the idea of using integrals to determine volumes. So this section is sometimes just entitled volumes or solids of revolutions. We're going to be a little bit more specific as we're going to be sort of focusing on a specific method in this video and its follow-up for section 6.2, which is called the disk and washer method. And we'll see as we develop this why we use this name here. So what is the main idea in this section? Well, in both sections 6.2 and 6.3, we're going to basically be trying to extend our study of integration, which from your previous calculus course and from section 6.1 has been used pretty much exclusively to study areas, either the area under a curve, between the curve and the axis, or between two curves, etc. And we're going to try to take that up a dimension and start studying the concept of how integrals can help us understand volumes. So to do that, though, we need to actually create three-dimensional shapes because volumes are a concept that are related to three-dimensional shapes, whereas areas are related to two-dimensional shapes. So the main sort of concept here is that volumes can be created by revolving areas around a given axis. So in other words, if you have some sort of area and you revolve it around an axis, if you basically spin it around, then that creates a three-dimensional shape, and we're going to try to determine the volume of those shapes. So to be a little bit more specific, we're going to consider this situation here. So suppose we have an area or region under a function f of x and above the x-axis from some x equals a to x equals b. And what we want to do is we want to revolve this area around the x-axis, creating a three-dimensional solid. What we're going to do is we're going to investigate how we can determine the volume of this solid. Once we've done this sort of exploration or this investigation, we'll then have a summary later on that'll show us sort of the formula that we're going to derive. But because I think it's it's pretty useful to see the derivation, and it also relates to some older topics with Riemann sums and things, it's a good idea to go through this exploration. So let's visualize what this setup is before we can try to figure out the volume here. So we'll just draw ourselves a little graph. Again, we don't know what f of x is, but let's just assume that it has a pretty simple shape. Maybe it looks something like that. So there's our f of x, and we're going to be assuming that we're going from x equals a to x equals b. So we'll say that those are sort of the ends of our interval. So we're only interested in our function there. And we're talking about the area under this curve and above the x-axis. So we're talking about all the stuff in here. Okay, now this, of course, you guys know how to calculate the area of that. That would be very simple. It would just be the integral from a to b f of x dx, and that would determine the area under that curve and above the x-axis. But what we want to do is we want to investigate a volume. So we're going to imagine revolving this around specifically in this case, the x-axis. Now, later investigations, we'll figure out how to move that axis. We'll learn how to revolve around like the y-axis or even a non-standard axis like an axis down here. But for now, we're just going around that x-axis. So what you want to sort of imagine is that this thing here is actually coming out of your page or your screen out towards you, then it eventually comes directly eye level with you, then swings back in, and then it's going to actually enter back into your screen or your page down here. We can actually draw that mirror image. At some point, it's going to swing down in here and sort of create a mirror image like that. And then it's going to swing back in, so it'd be sort of behind your screen or behind your page, and then come back around and form a 3D shape. So if we indicate that, we can sort of say that it's going to look something like that, and it'll look something like that. So it would be this sort of piece like this. And because we're revolving that as an area, in other words, we're not just revolving this curve, we're revolving this entire area, all of this stuff is filled in. So this is actually, as the name would imply, a solid of revolution. So we're not just getting the outside. We're not just taking this curve and bringing it around, but we're bringing in along everything in there. So all this stuff is filled in. So this is a solid. The shape of this, I guess, would look sort of like a sort of weird table or something that's been turned on its side or something like that. This is a solid shape, so this is not like you can put your hand through this thing or anything. All of this is one solid shape. And what we want to try to do is we want to try to determine the volume of this solid. So this is sort of what we're going to be working on here. All right, so how can we investigate actually trying to determine the volume of this? Well, let's go back to our sort of basic roots with this with sort of an approximation. When you guys first learned how to determine the area, you sort of used a Riemann sum approach. So let's do something similar here. we'll redraw so that we sort of can look at this. And again, we sort of now know the main idea. So there's our curve. There's the moment where it sort of comes around as the mirror image, and then we know that this makes an actual sort of 3D shape. And then we know that this here, this is our x equals a, and this is our x equals b. All right, so what we're going to do is let's see what happens if we do sort of an approximation. Let's take a shape that's very nice and easy. When you guys did areas, you started with rectangles. So let's build some approximating rectangles. So maybe we take a rectangle that starts here and goes over a little bit, and then we take another one that goes here, goes over a little bit, and then over a little bit, over a little bit, over a little bit, and then finally we get a last one there. Now, when you guys did this, we'll zoom in a little bit so we can sort of see this. What we would say is that each of these, we could say has width delta x. Okay? And let's think about what happens when we take one of these rectangles and revolve it around. So if we just cut out a single one of these rectangles here, so let's just imagine we've got our single rectangle, and there's our axis, and remember we're going around this thing here. Okay, so let's imagine we have its mirror image down here, and if we think about that as a 3D shape, there we go. What sort of 3D shape is that creating? Well, that's creating is, if you revolve that rectangle around, this is creating a cylinder. Okay, so that's nice because in terms of volumes, we might not know a lot of volume formulas, probably know how to like calculate a volume of like a sphere, maybe a cube, things like that, but a cylinder is certainly something we know how to calculate the volume of. So, what is the volume of a cylinder? Well, we know that the volume of a cylinder is pi r squared h. Right? It's pi times the radius squared times h. So, let's go ahead and label on this sort of diagram here. Right? We'll just use a different color here, maybe a nice green or something. Right? Let's go ahead and label where this radius and this height are on our diagram. It's a little bit weird because this is actually a cylinder on its side. So keep in mind that the radius is actually this distance here, and the height is actually this distance here. So the cylinder is on its side, so the height is there and the radius is there. Okay, let's see if we can then talk about the radius and the height based on our information here. Well, as we can sort of see, let's focus maybe on the radius component first. The radius is going to be the height of these rectangles. Now, if you guys remember back to sort of when you're doing sort of Riemann sum, since this was just an arbitrary one we sort of cut out, usually we use that sort of notation as being like this is like x sub I. It's some arbitrary x sub I along the way as we're cutting this up into pieces. So the height of the rectangle is the function evaluated at that x sub I. So we can sort of recognize here that our radius is going to be our function evaluated at whatever point we're looking at, whatever x value we're currently at as we're going along and doing our approximation. What about the height? Well, the height is this distance. It's sort of that horizontal distance. That's the width of each of these rectangles, which we know is delta x. So we know that the radius here is going to be delta x. So that tells us overall that this volume can be thought about as pi f of xi squared times delta x. So the volume of one of these cylinders is equal to this. Now, of course, the volume overall approximately is the sum of all these. So we can now say that the overall volume is approximately, we have to say approximately because obviously these rectangles only approximate the area, and certainly they only approximate the volume here. So that we can say that the overall volume is approximately the sum over all the different xi of all of these volumes of these individual approximating cylinders. So we would say approximately, lost my color there we go, pi f of xi squared delta x. So that's our volume. If we sum up for each of the xi's for however many partitions we have, then we can say that our overall volume is at least roughly the sum of all the volumes of each of these different cylinders. So this is an approximation. How do we make it an actual equality? Well, as we know, you can take the limit. If you take the limit as that delta x, as those approximating rectangles get infinitesimally thin, then you can make that, instead of just a approximation, you can make it an equality. So we can say then that the volume is actually equal to the limit as delta x goes to 0 of the sum of those xi, pi f xi all squared. Probably better to actually put parentheses there. Delta x. All right, now when you take a limit of one of these sums, that is a Riemann sum. And we know that this can be converted into an integral. So this tells us that the volume is the integral. Where are these xi's being selected from? Well, they're being selected from x equals a all the way up to x equals b. So it's the integral from a to b, pi. This is not f of x, it's f of x squared. So we get pi f of x squared. And notice we no longer have to say at each xi, because now we're doing a definite integral, right? We're not just taking a sum of a bunch of approximations. We're not selecting xi's. We're using x as it tends from a to b. And then, as you guys probably remember from 190, that delta x then becomes your differential, your dx there. So we've just figured out that the volume can be viewed as the integral from a to b, pi f of x squared dx. All right, so this right here gives you guys a basic derivation of our first way of calculating the volume of a solid of revolution. Just to recap, the case that we're in right now is exclusively in the situation where we have a function of x from some x value to some x value. We take the area underneath there. We revolve it around the x value, creating this solid. Our approach thus far has been to use approximating rectangles. When those approximating rectangles are revolved, they become these cylinders. We determined the radius. Oh, and we have a little mistake here. I'm sorry. That should be the height there, h. Right? My apologies. We have the radius and the height right there, which allowed us to determine the volume of each of these cylinders. If we combined all those cylinders together, then we got an approximation for the overall volume. We changed that approximation into an equality by letting the limit of the width of each of those rectangles, which was the height of each of those cylinders, approach 0. And then that we were able to convert this Riemann sum into an actual definite integral. It is not a coincidence that if you look at this, this sort of should remind you of pi r squared in here, because if you imagine smushing these cylinders down to something that is infinitesimally thin, where that delta x has gone to 0, you're basically imagining slices of this thing that are each circles. And the area of a circle is pi r squared, and when you integrate an area, you get a volume. So there's a lot of things sort of behind the scenes here. Okay, so this is our derivation here. Let's go ahead and summarize this so that instead of having it all sort of messy like this, we can jump right to what this sort of expression that we derived here. So, all right. Overall, we can summarize this by saying, let's suppose you have a function f of x from x equals a to x equals b, and we suppose you revolve the area under this curve and above the x-axis around the x-axis. Then what we just derived is that the volume of the resulting solid can be found by the integral from a to b, pi times f of x squared dx. And again, just so you guys can reference, the diagram here is if you are in the situation where you have some curve like that, f of x, and you're going from a to b in terms of x, and you're taking that region and you're revolving it like that, you're creating a solid that looks like that. And you can determine the volume of that thing using that equation. Okay, now we could go ahead and redo everything we just did from the y perspective. So we could instead talk about what happens if we have a function of y and we go around the y-axis. It shouldn't be a surprise that this is completely analogous, so I'm going to do this without having to go back and rederive. Instead, we're just going to state it. So we do get a second sort of follow-up from the y perspective. So if we redid everything we just did from the y perspective, we could suppose that we have a function g of y from y equals c to y equals d. So now we're sort of imagining there's our, so now we have maybe some curve that looks, maybe it looks like that or something. We'll call that g of y. Now we're thinking about it from y equals c up to y equals d. So we're thinking about it in terms of y. If we revolve the area between this curve and the y-axis, so if we talk about taking this stuff in here, and we revolve that around the y-axis, so not taking it around the x-axis, not taking it down here, but actually taking it around that y-axis. So if we revolve here, then of course what that would create is you would get sort of a mirror image over here, and it would create a shape that sort of looks maybe something like that. And you would be able to determine the volume of that solid with a very similar expression. The volume would be the integral from c to d, pi times g of y squared dy. So once again, same format, but difference here is that we'd be treating it as a function of y, and we'd be revolving around the y-axis. Notice also the region or the area that we're talking about is no longer the area under the curve and the x-axis, but the area between the y-axis and the curve. So it's sort of the area to the right here. Okay, so we've developed sort of two basic formulas, one in terms of x and one in terms of y. Now, in a moment, we're going to go ahead and take a look at a couple of quick examples. But before we do that, I want to mention what we still have to do in this section 6.2. There's two big limitations with these initial two formulas that we've done here. The first sort of limitation is that in both of these, we're assuming that we have the entire area either below the f of x or sort of to the left of the g of y. As you guys know, though, from section 6.1, sometimes we're interested in areas between two curves, and we might be interested in a solid that's created by revolving the area between two curves. So we need to understand how to sort of approach this if our area doesn't reach all the way to the axis. The other thing that we still need to determine, again, which we'll be doing in the next video, is going to be what happens if we have a non-standard axis. This talks about what to do when we go around the x-axis or the y-axis. But we shouldn't be limited by that. Maybe we want to revolve around an axis like down here. Maybe we want to revolve this thing all the way down here and make some giant shape. Or maybe we want to take this thing and revolve it around an axis here. Those are very similar to the x and y axis, but we'll need to develop a little bit more theory to deal with them. So those will both be considerations that we cover in the next video when we wrap up 6.2. For now, though, let's go ahead and just make sure we do at least one example of each of these formulas just to understand the basics here. All right, so for our first example, we're going to try to determine the volume of the solid created by revolving the area under y equals e to the x and above the x-axis from x equals 0 to x equals 1 around the x-axis. Now, this is just our first example of a solid of revolution. We are going to do a bunch of these as over the next few videos. Something I want you guys to understand, though, is that there's a lot of information that is given in a single problem here. You have to first be given an actual region, meaning that you have curves that are defining that region, y equals e to the x-axis, x equals 0, x equals 1, and you have to be given the axis around which you're revolving, in this case, around the x-axis. Solids of revolution are definitely a little bit more complicated than calculating areas. For areas, we always wanted a diagram, and we definitely always want a diagram for solids of revolution as well. So let's go ahead and draw that here. So for this one, we'll give ourselves a nice sort of big axis. We know we're talking about x equals 0 to x equals 1. So there we go. And then I guess we can go like 1, 2, 3. Our curve is e to the x. So we know that that starts at 1. And by the time we're at 1, we're at e, somewhere up there. And there's our exponential looking curve. And there's our region, if we want to sort of shade that stuff in. I think I prefer the blue here. Okay. Then let's also indicate what axis we're going around. So there's our axis. We can go ahead and I do always recommend drawing in at least the mirror image. You don't necessarily have to try to draw in what the solid looks like, but I would definitely draw in the mirror image. There we go. And something down there. And there we go. And of course, all this stuff is going to get filled in as well. Okay. And again, we could sort of actually draw it in. It's going to have that sort of table shape that we are looking at. But I'm not going to try to, I mean, you could draw in this piece and this piece to really visualize the three-dimensional part. But I find that makes generally the graph a little messy. All right. So let's go ahead and see if we can determine this volume here. Well, I think it always helps to sort of give a representative sort of slice that we're using here. So let's imagine sort of a representative piece there. There we go. Again, I'm making it infinitesimally thin. That part there is being reflected to there. That's giving us that circle, or what's often referenced as the disk. And then we are compiling all those infinitesimally thin disks together, sort of a slice there, slice there, slice there, slice there, slice there. And then that's giving us our whole volume there. So if we go ahead and do that, we know that the integral is going to be, well, we can choose these little disks here anywhere from x equals 0 to x equals 1. So we have the integral from 0 to 1. Pi. What is going to be the radius of this disk? What is that function? Well, it's going to be up to that e to the x. So e to the x. Notice it's technically measuring e to the x to the x-axis, which is e to the x minus 0. But of course, that's just e to the x. And then squared. And then dx. Is that exactly what the formula would have told us? Well, if we look back, the formula tells us the integral from a to b pi f of x squared dx. Yep, that's exactly the formula. So why didn't I just plug into the formula? Well, again, as things get more complicated, you're going to want to make sure you understand where the formula is coming from. So in case we have a situation where we're doing between two curves, maybe there's another curve there, or maybe the axis is actually floating down here, you understand where the components are coming from. And again, in this method, this right here, which is the really important sort of piece, it's really determining the radius of that sort of disk. And the radius here is stretching from here up to there, which is from the x-axis up to that function, which is just the e to the x there. Can we actually determine this volume? Yep, pretty easily. And we can say that that's the integral from 0 to 1 pi e to the x squared. Well, we can simplify that. That's just e to the 2x dx. That actually will be a u substitution. So let's go ahead and u equals 2x because we have a composition there. Our du is going to be 2 dx. We do not have 2 dx, so we'll have to do 1/2 du is dx. But do keep in mind this is a definite integral, so we should go ahead and change our bounds. Bounds were 1 and 0 in x, so in u they're going to be 2 and 0. How do I know that? Well, because u equals 2x, so 2 times 1 is 2, 2 times 0 is 0. So we now have that the volume here is the integral from 0 to 2, pi e to the u, and we have 1/2 du. We can actually go ahead and do that. That's going to give us 1/2 pi e to the u, because the integral of e to the u is e to the u, evaluated from 0 to 2. So it looks like our volume then is 1/2 pi e squared minus 1/2 pi e to the 0, which I suppose if you factored, you could call like 1/2 pi e squared minus 1. So there we go. We determined the volume of that entire solid there. Quick check, always remember volumes, just like the area between curves, we're actually talking about the geometric volume. We're treating this thing as a solid. So this has to be a positive value there. If you ever get a negative value, then something's gone wrong either in the setup of the integral or of the integration, because everything's got to be a positive value here. Okay, so that's determining the volume of our first solid. Nice and simple here, but very, very important that you sort of can see what we're really doing is we're taking all these disks, all these thin disks, putting them all together sort of like slices, and then building our shape. And the area of each of those disks, area of a disk or area of a circle is pi r squared. When we sum all those up or integrate all those together, then we're actually creating that volume. Okay, let's try one more quick example from the y perspective. So for this one, we want to determine the volume of the solid created by revolving. Some terrible misspelling there, right? Revolving, but we mean revolving. The area between x equals y squared plus 1 and the y-axis from y equals 0 to y equals 2 around the y-axis. So once again, the information here is a little dense. You've got an area created by a curve, another curve, and some boundaries. And we want to go around the y-axis in this situation. So let's go ahead and draw this out. Okay. So we know y equals 0 is going to be an important boundary, and then 1, 2. I guess we know y equals 2 is going to be an important boundary. Okay, we can give ourselves some x values. 1, 2, 3, 4, 5, 6. Okay. What does this guy look like? Well, x equals y squared plus 1. That's a parabola, but in the y direction. So remember, you're sort of plugging in y values and then getting x values. So that looks like when y is 0, we'd have x is 1, so we'd have a point there. Then when y is 1, x is 2, so something there. And then when y is 2, x is 5, so 1, 2, 3, 4, 5. So something like that. And there's our curve. If we drew out the whole thing, of course, it would look something like that, because it's a parabola in y, but of course we only need this portion here. And we want the stuff between this, the y-axis, y equals 0 and y equals 2. There's the y-axis. There's y equals 0, there's y equals 2, and there's our curve. So we're talking about this stuff in there. Okay. And what axis are we going around? Well, we're going around the y-axis here. So that's going to create a sort of mirror image over here. Something that looks like that. And if we wanted to, you could say that there's the top, there's the bottom. This guy should extend further out, but I sort of ran out of space, but there we go. So, and of course that's going to bring this stuff over to here as well. Okay, so there we go. All right, let's go ahead and think about how we're going to do this. We're going to be working with respect to y here because the function is in terms of y, and we're going around the y-axis here. So let's think about what one of those representative disks would be. You're choosing a y value, sort of going out to your curve there. That's being revolved around here, and that's creating that disk. So the disks this time are like this. You're stacking them up from here on top of each other. They get wider and wider. Their radius gets larger and larger, and that fills in the entire picture there. Okay, so what is our volume here? Well, it's going to be an integral. In terms of the choices, well, these slices could happen anywhere from y0 all the way up to y equals 2. So our boundaries are going to be 0 to 2. Pi. What's the radius of these slices? Well, we're measuring from here to here, which is we're measuring from the y-axis to this function of y. So it is just going to be that function of y. So y squared plus 1 squared. And then, of course, we're integrating dy here. So there we go. There's our expression for the volume of this shape here. How do we actually determine this volume? Well, we'll have to sort of expand it out. This is the integral from 0 to 2, pi. Looks like we get y to the 4th plus 2y squared plus 1 dy, which we can say is pi times, and then looks like inside we get 1/5 y to the 5th plus 2/3 y cubed plus y, evaluated from 0 to 2. And looks like we should get pi times, well, looks like 32 over 5 plus 16 over 3 plus 2 minus 0 when we plug in the 0 there. And there we go. There's our volume. I suppose if you wanted to, you could simplify it a little bit. You don't really need the 0. Volume is pi times 32 over 5 plus 16 over 3 plus 2. So there we go. That would be the volume of this shape here. Okay, so right there, you guys got to see 2 examples of what is considered the disk method. It's a disk method here because, again, what we're doing is we're building these infinitesimally thin cylinders, which really are disks. We're stacking those disks together to build these volumes. In the next video, we'll continue doing some examples using this method, but we'll add 2 extra complications. One is that we might not have the full region all the way to the axis, so maybe we'll introduce like another curve here and we'll just be interested in revolving this stuff. And we'll also change these axes, so we won't always just have to revolve around the x or y axis. So we'll see those in the next video.